Okay, well, let's continue. I heard, I heard something, but I'm not sure what it was. Uh, okay, well, if it was something related to what we're talking about, could could the person who made the sound repeat it again? Well, if it wasn't, then probably probably doesn't matter. Well, there's an obvious example of a spectrum which is a suspension spectrum, and my guess is that everyone knows what a suspension spectrum is. If this guess is not correct, please let me know. And there is another example which will be more relevant to us: Thom spectra. Now, does everyone know what the Thom spectra are? Well, let's take the universal bundle over the. Let me let me change let me change the indices. Let me put a k here and n here. Well, there are Grassmann manifolds which are probably familiar to everyone, and there are universal bundles over the Grassmann manifolds. So we have we have the following diagram which commutes. Uh, does this diagram make sense? Again, if it doesn't, please protest. Otherwise, there is no way for me to know that it doesn't.
What is E? The curly E that you add on? No, not that. Not that one. The other one. E of gamma plus curly E.
Oh, yes. This is the trivial rank 1 bundle.
Mm-hmm. So you're just saying if I pull back the trivial rank K, the tautological rank K plus 1 bundle along this embedding,
Yes.
then I get the tautological rank K bundle plus an extra trivial factor.
Yes. Well, I didn't say what the embedding is. The embedding is as follows. We'll take a K plane in Rn plus 1. Sorry, in Rn. And then we add the n plus first basis vector, and we get a K plus 1 plane, but this time in Rn plus 1. And this is why the restriction splits as a direct sum of the tautological K bundle plus a trivial summand. And so we get a map of the Tom spaces. And the one on the left is the suspension of the Tom space of gamma chi n. Now, does this make any sense? By the way, where does the formula for the Tom spaces come from? Why do we get a suspension?
В произведении пространственном.
Произведение пространственного.
Because when we take the thumb space of sum, we get the smash product of thumb spaces.
Say again?
Thumb space of a sum is a smash product of thumb spaces, and since the thumb space of a one-dimensional trivial bundle is a circle, this precisely is a suspension.
Not quite, but almost. Suppose we have two vector bundles. On not necessarily with the same base. the base spaces may be different. Then the formula is the Thom space of the Cartesian product, not the direct sum of the bundles, is the smash of the Thom spaces. Now let's look at this formula again. What is the direct sum? The direct sum is the Cartesian product with the trivial rank 1 bundle over a point, and hence and the Thom space of the latter is just a circle, and hence we get this formula. Okay, now so the Thom spaces of the Thom spaces of the tautological bundles form a spectrum. And this spectrum is relevant for well, it's basically the main object in cobordism theory, but we'll need a slightly different spectrum.
Can one say, I've never really understood this. So, okay, you construct a spectrum, you do some calculation with it, you see cobordism groups, but I mean, what is the Thom spectrum really? What's it doing? Okay, I'm from some alien planet, and all I know is kind of abstract homotopy theory. Is there a way to say what the Thom spectrum is in those terms?
I don't know, but there are well, apart from calculating the cobordism groups, one other point is that if you take BU and just BU, well, BO is not very interesting. It's basically cohomology mod 2 with it's basically lots of copies of cohomology mod 2. BSO is incomprehensible, but BU is somewhat comprehensible, and it sees some things which the standard homology doesn't see, and that's the point of having it.
But can we just say that the Thom spectrum presents the Lazar ring as homotopy groups, and that is uniquely determined by this universal property of the Lazar ring, something like that?
Well, I don't know. Does it make sense for extraterrestrials?
Well, there's a description of it in terms of some kind of a duality, right?
Well,
is that correct?
Well, a duality is the way I understand it is basically the Poincare duality of the spectra.
Mm-hmm.
There's it's not specifically related to Thom spectra. It works for all spectra.
Okay. Anyway, we can continue.
Okay. Okay, so let's define a slightly different spectrum.
Sorry, I looked it up, what I was trying to remember. So the statement I was trying to remember is if you have a compact smooth manifold, there's a suspension spectrum. And you can compute this as Thom spectrum of stable normal bundle. And so this is a statement of a Tia duality.
Is it? Okay.
This is the claim.
Well, by the way.
Okay. Anyway, we can continue.
If we need a lecture on spectra, please let me know, and then we'll maybe have someone talk about that. But otherwise, if we don't need, let's not
continue.
Have it.
Okay.
So we'll need a variant. Okay, well, I will gamma. Okay, so instead of the tautological bundle, let me take the orthogonal complement. Okay, let's see if is it the right notation? Yes, K upstairs and downstairs. Okay, so the orthogonal complement. Orthogonal complement where? Well, inside the trivial. Inside the trivial rank n bundle. So this time we have a slightly different diagram. We have gamma k of Rn which will go to gamma k of Rn plus 1. And this time the map is simply induced by the inclusion of Rn in Rn plus 1. Nothing fancy. And we have a similar diagram. Let's draw it. I take the orthogonal complement plus epsilon, and I take the gamma k n plus 1 orthogonal complement. So the inclusion is induced by Rn inside Rn plus 1. Does the diagram make sense? Now, if the diagram doesn't make sense, please don't keep it to yourself. Let everyone know. Okay, now the strange notation. So before I explain the notation, let me just say that the same works in the oriented case as well. And we will need for oriented diffeomorphisms, we will need the oriented version. Well, no surprises there. Okay, now now let's explain what the notation in the in the Madsen-Weiss theorem means. Sorry. Before I put a plus here, let me explain what this means without the plus. Well, well, this means A, G, and K stands for the space of affine K subspaces of Rn, where affine means they don't necessarily contain the origin. Well, let's see what this space is. This space is precisely the total space of the orthogonal complement of the tautological bundle. Does this make sense?
You mean, does the statement make sense, or do I understand why it's true? So let's see. What is the orthogonal doing?
Well, if we have a plane through the origin, then all possible affine planes with the same tangent space are parameterized by the orthogonal complement.
Basically, you translate in the orthogonal direction.
Yes.
Uh-huh.
So suppose I have a line through the origin, then what are the affine lines with the same underlying vector subspace? Well, these are all translations of the vector line in yeah, through
Okay.
by elements of the orthogonal complement.
Okay.
Okay, so in particular, we get maps. Well, I'm going to use that notation in a moment, but it's the notation Hatcher uses in his notes. So to make it consistent, I will use it as well. But the notation is that. Why is it bad? Well, plus normally means the space plus a disjoint point. Well, here we want to use the one-point compactification. Well, the base space of the bundle gamma kn and also of the orthogonal complement is compact. So the one-point compactification of the total space is the same as the Tom space of the bundle.
Okay.
Well, these spaces for a fixed k and varying z form a spectrum. Well, why? Because of this diagram. Okay, now we understand which spectrum the Madsen-Weiss theorem talks about. Except we don't know what omega infinity is. Now. Now, suppose we have a spectrum and we want to define homology theory using the spectrum. If we proceed in a straightforward way, this doesn't work. But for omega spectra, it does work, and the question is there a way to obtain an omega spectrum starting from an arbitrary spectrum? And there is. Let's see. So my claim is, starting from the way this is no, I want. I want to put an I here and plus I. Okay, what's what if anything does this mean? Well, I have an arbitrary spectrum. Suppose I have an arbitrary spectrum. Then I have maps from xn to omega xn plus 1, and then from here to omega square xn plus 2, and so on. All these maps are given to me by the structure of the spectrum. Now, it says how Colin. What does this mean? Well, this means in this particular case, this is simply the telescope. Now, what does this mean? Well, suppose I have a sequence of spaces and maps. Then I can take all cylinders of these maps and join them together. Oops, this is not it. And the result is called the homotopy co-limit of the sequence, which is the same in this particular case of the telescope. Do I need to say anything something more about telescopes? Well, the picture is self-explanatory. It sort of looks like a telescope. Is it clear? Is it clear what the telescope means? What the telescope is?
Oh, I actually thought that we need to draw some other cylinders, like between the start of this telescope and like the second stage. So So it's not enough to just draw what you drew, but also we need like cylinders between the first space and like the third space. No.
No. Well, the result is homotopy. Well, I think the result will be a homotopy equivalent. There is no need to have more cylinders.
So I don't remember what the answer is, but the place you look for an answer, it's about different kinds of diagrams require different kinds of resolutions. So it's you have to somehow apply, what is it, Coulomb theorem A or B in order to convince yourself that you've properly resolved the diagram.
Well, yes, exactly. Couldn't theorem A. The difference will be the same as between fat realization of simplicial set and usual realization of simplicial set. Whether you add those additional cylinders or not.
Anyway, my claim is
homotopically is the same.
Yeah. I understand that this semi-simplicial category is homotopy initial in the simplicial category, but I was just confused because I saw this picture of like in Dagger's survey that you need to draw this, but yeah, I guess you're right. I'm sorry.
Anyway, my claim is the homotopy co-limit of this diagram is just the union of cylinders, and there aren't any more cylinders. If you want to put more arrows in the same diagram, you will need to draw more cylinders, but we don't need to. Okay, now the question is why do we have why do we get an omega spectrum? Well, let's see. So we have x prime n, which is the well. Let me say. Let me use the same. Okay, we're running out of time. Okay, let's erase this part. Okay, let's quit and join the meeting, and then I'll explain why the result is an omega spectrum.